In this section, we introduce a general idea of geometrically constrained methods. This method can be applied to high-dimensional sequence or dynamic learning tasks, such as forecasting models that jointly incorporate power and temperature features. We start from the observation that many dynamic systems involve a low-dimensional manifold embedded in a higher dimensional ambient space. As illustrated on the left, although the ambient dimension is 3, the intrinsic dynamics actually lies on a two-dimensional manifold. For the true system, the dynamics is represented as dot x equal to fx. For the traditional data-driven methods, they directly learn an unconstrained approximation dot x height equal to f height, which may introduce surprise components that drive the state of the manifold. To address this issue, we introduce a geometrically constrained model x height equal to p times f height, where the learned vector field is projected onto the local tangent space. The projection matrix defined as P equal to T times T transpose. Here, the tangent space T is first estimated using local SVD of the neighborhood around each data point. This provides a first-order approximation of the manifold geometry. To further improve accuracy and robustness, especially under noise, we employ the GMLS method to refine the tangent basis by incorporating high-order local information, as shown in the figure. This allows us to model not only tangent increments, but also the corresponding normal correction as the second part in this formula. Detailed model of a function g, which is a GMLS model, is given here. More information can be found in this reference paper as shown below. In this subsection, we present an implementation of the geometrically constrained model on the multi-output KRR. We began by extending the standard scalar output regression to a vector-valued mapping, where the output is the system velocity. The derivation of the multi-output KRR model is given below. The optimization minimizes the data mismatch with an L2 regularization term, resulting in a closed-form solution. Similar to the scalar case, the primal solution admits an equivalent dual representation, where predictions still depend only on kernel involution between the query point and the training samples. This yields a compact prediction model expressed through the kernel matrix K. Next, we introduce the geometrically constrained extension, denoted as the GMKR. The key idea is to enforce that learned vector field lies in the local tangent space of the data manifold. This is done by inserting the projection matrix P into the feature mapping, which effectively modifies the kernel into a geometry-aware kernel. As a result, the original kernel K is replaced by a G-constrained kernel, which incorporates the tangent basis Ti and Tj at the corresponding samples. This leads to a structured kernel matrix that can be factorized into no-dimensional components, significantly reducing computational complexity while preserving geometric consistency. Finally, the prediction takes the same closed-form structure as standard KR, but now the output is guaranteed to respect the manifold geometry. In this slide, we present a numerical validation of the geometrically constrained KR method. We consider a no-dimensional benchmark problem with ambient dimension n equal to 2 and intrinsic dimension d equal to 1. The underlying dynamics are defined on a one-dimensional manifold, governed by this equation, for which an analytical solution is available. To embed the system into a high-dimensional observation space, we map theta into Cartesian coordinates using a radius function as shown here, where the parameter d controls the strength of geometric distortion. Next, for data preparation, we generated trajectories with a fixed time step delta t equal to zero point zero 0.04. Only the first 200 samples covering about 1.5 cycles are used for training, while the entire trajectory is used for testing. The model parameters, including kernel bandwidth, GMLS order, and the tangent space dimension, are selected via validation for each D. On the right, we show the prediction results for different distortion levels. In contrast, the proposed geometrical constraint KR with normal correction remains stable and accurately tracks the true dynamics across all cases. The quantitative error table further confirms that the proposed geometrical constraint methods outperforms the traditional RK2 and neural ODE, and is also more stable than AOD-NAT. Finally, the time comparison shows that the proposed geometrical constraint methods achieves this accuracy with significantly lower training cost, making it well suited for computationally constrained scenarios. That's all for this section. If you are interested in this method, please learn more about it from the reference paper. That's all, thank you.